Today we are graphing radical functions, specifically the square root function. So the square root function is a function that contains radicals with variables in the radicand. So specifically today we're talking about the square root function, which is a function that contains the square root of a variable expression. Our parent function is f of x equals the square root of x. So because the square root of a negative number is non-real, you'll see that it begins at 0, 0, and we only have positive x values. The square root of 0 is 0. You can see we have the 0.42. If you were to substitute 4 in for x, the square root of 4 is 2. So it is increasing when x is greater than 0. And then it's positive for values greater than 0, and there is no symmetry. The general form for a square root function is g of x equals a times square root of x minus h plus k. A is a vertical stretch or compression, and if a is negative, it's reflected in the x-axis. H is your horizontal shift, and k is your vertical shift. So to graph the function, f of x equals square root of 2x minus 6 plus 1, we have to restrict the domain because remember, we can't take the square root of a negative number, or the square root of a negative number is not real. So the expression that's under the radical sign must be greater than or equal to 0. So to solve this for x, I add 6 and then divide by 2. So x values, our domain, is greater than or equal to 3. So 3 is where this graph starts. Let's see what the y value is when we substitute in 3 for x. So 2 times 3 gives us 6. 6 minus 6 is 0. And the square root of 0 is 0. And then we add 1. So 3, 1. So our domain is x such that x is greater than or equal to 3. And the range is f of x such that f of x is greater than or equal to 1. To graph that, okay, so now we have a new example here. A is negative 3, so it's going to be reflected. We're x minus negative 1, so we're shifting left 1, and then plus 2, so up 2. So first we're going to determine the minimum domain value, so that comes back to whatever we have under the radical sign must be greater than or equal to 0. So x must be greater than or equal to negative 1. So we're starting at negative 1, and I just am going to type this into my calculator to find the corresponding y values. And then we are going to plot those points. So starting with our domain has to be x values greater than or equal to negative 1. Range is g of x is less than or equal to 2. So notice when we starting at negative 1, the smallest value we could have under for x, we get 2, and then our y values, notice, are decreasing from there. So I'm plotting negative 1, 2, 0, negative 1, 1, negative 2.2, 2, negative 3.2, and 3, negative 4. And we'll connect them. We just have an arrow on the one side because there aren't any points. The function is not defined for anything less than negative 1. And then comparing that, so our maximum value was negative 1, 2. A was negative 3, H was negative 1, and K was 2. So it was vertically stretched because the absolute value of A is 3. H was less than 1, so we translated left H units, and K was, or left 1 unit, and then K was greater than 0, so it was translated up 2 units. Example 3. When blood is donated, medical professionals use a centrifuge to separate it. The centrifuge spins the blood, causing it to separate into 3 components, which are red blood cells, platelets, and plasma. In order to efficiently separate the blood, the centrifuge must spin at a specified rate, measured in rotations per minute. For the required gravitation force, or G-force, exerted on the blood, For a centrifuge with a radius of 7.8 centimeters, the RPM setting of the centrifuge is determined by the product of 104.23 and the square root of the g-force required. All right, so we've translated that here in this table. R equals 1.0423 times square root of g. So we could type that into our graphing calculator, generate a table, and then also a graph. So let's take a look at the range. So you're looking at your y values. We would never have a negative y value when we're measuring RPM. So R is greater than or equal to 0. Our x-intercept, so where it crosses the x-axis, is at 0. The y-intercept, where it crosses the y-axis, is also 0. It is increasing as g approaches positive infinity, and it is positive for g greater than 0. For our end behavior, as g approaches infinity, r approaches infinity. Next, we are going to graph a square root inequality. So first, we're going to start by graphing the related boundary function. So because it's less than, we will use a dashed line or curve. So I did type it into my graphing calculator, y equals square root of 2x. And then I looked at the table, and then I will plot the points from the table. So I'm going to plot negative 2, 1. Or negative 2.50, I guess, because that's where x would start. So 2x plus 5 has to be greater than or equal to 0. So that's where the negative 2.5 came from. And then the other points came from the table in my graph. All right, to shade, we will shade below because it was y is less than. And then testing 0, 0 to make sure shading below gives me a true statement. If I substituted in 0 for x and 0 for y, okay, 2 times 0 is 0, plus 5 is 5, and then the square root of 5 is approximately 2.24, so we get 0 is less than 2.24, which is true. So we will shade below that because 0, 0 was below that curve. Thank you for watching.